Hi, welcome to Pre-Algebra lesson 10-1. We'll look at the overall topic first. So topic 10 is about solving problems involving geometry. The topic essential question would be, how can geometry be used to solve problems? So this is all about geometry. Look at the topic vocabulary: adjacent angles, circumference, complementary angles, composite figure, cross-section, scale drawing, supplementary angles, vertical angles. So if you are the one who loves a shape, you are good with problems that involve areas and volumes and shapes and different angles and drawings, this is for you. So the topic overview gives you all the lessons here, the title of all the lessons. The lessons are from 1 to 9. It's all about problems involving scale drawings, geometric figures, triangles, angle relationships involving circumference of circle, cross sections, surface area, volume. So if you have learned geometry before, this is a little bit more in depth. And in Algebra 1, geometry topic is also going to be a little bit more in depth. So if you enjoy this, you'll enjoy this topic. Let's look at the intro for let's look at page 583 here. Review what you know. We'll start with what we know. So let's look at the vocabulary that we know. The number of square units that a figure covers is its blank. So we're talking about the square units. It's a 2D, right? So a 2D, what's it called? This that covers the shape. This is the area. Okay, and then the blank of a triangle is the length of the perpendicular line segment from a vertex to the opposite side. So one vertex to the opposite side. What is this called? The height of the triangle, right? So the height of the triangle. The blank of a solid figure is the number of cubic units is needed to fill it. So this is 3D. What is a solid figure's 3D that's needed to fill this? This is called the volume. Any line segment that connects the center of a circle to a point on the circle is called so in the circle, any segment that connects the center of the circle to any point on the circle, this is called the radius. Okay, so these are the words that you probably have heard before. There's also base and diameter. So diameter would be the length around the circle, and then base of a triangle would be this, like the base on the bottom. So let's look at area and volume problems that we have learned so far. Area of triangle with a base 6 feet and height 9 feet. So you have a triangle and you have a base 6 feet here, and then height is 9 feet, right? So the area would be base times height divided by 2. So you're going to multiply 9 and 6 together, divided by 2. 9 times 6 is the area of this triangle, which is 54 divided by 2, which is 27 feet squared. Don't forget that your units are in square for a 2D area. Volume of a rectangular prism. So we have a prism that has rectangular sides with length 4 inches, width 2 inches, and height 2 inches. So height is 2 inches, width is 2 inches, length would be 4 inches. The volume is length times width times height, right? So you just multiply all of this together. 4 times 2 times 2 is 8 times 2 is 16 inches cubed. So cubic inches. Let's look at angles here. If you have a protractor, you can measure it, right? Using a protractor, I can't show you my protractor, but using a protractor, you should be able to measure this angle, which is going to be 55. If you measure this angle, you know that this is 90 degrees, right? This is 90 degrees, and it's a little bit over 90 degrees here. And if you have a protractor, you'll see that it's 105 degrees. Let's look at number 9. Describe this figure using as many geometry terms as you can. Okay, so what is this shape? You know that all angles are the same, so it must be a rectangle, right? You know it's a rectangle. Is it square? You don't know because you don't know if the lengths are all the same. We just don't have enough information, so we can't say it's a square. This is a polygon because it is a closed figure made up of line segments called sides. So these are sides, and then these are angles or right angles, right? The points here, these are points, and the measure of each angle is 90 degrees. The rectangle is a type of parallelogram. So the line segments AB and DC are parallel. Line segments AD and BC are parallel. So AB is parallel to DC, and AD is parallel to BC. Okay, so these are some terms that we could have used to describe this polygon. Let's go to the next page. We have language development. Fill in the word web to connect keywords you learned in this topic. So we have one corner here that's all about angles. We have adjacent angles, vertical angles, complementary angles, supplementary angles. Yeah, you can use this word web to connect keywords and help you visually display the meaning-based connection between a word and a set of related words or concepts. So we'll have a lot of different concepts here. You can fill this in as we go through the lessons in this topic, okay? Yeah. So let's get started with lesson 1. Solve problems involving scale drawings. In this lesson, you'll be able to use the key in a scale drawing to find missing measures. So, how can you represent a relationship between the model of the plane and the actual plane? So in the picture, you have a model plane, and then you have the actual plane. And if this model, it models exactly as this airplane, but it's just smaller, you know that it's proportional, right? So, yeah, they have a proportional relationship. And so you can use unit rates to figure out the relationship between the lengths. I'm going to say I can draw a diagram to relate the length of the model plane to the length of the actual plane. So yeah, it's asking us how to represent. So you can either use a diagram, table, or proportions. Okay, so if you draw a diagram, you could probably draw yeah, something like a table. So table is also like a type of diagram, but a diagram, for example, you can have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So yeah, if this is 1 inch per box, we can say that this is 15 inches, but we can say that there is a length that is proportional to 15 inches, which is 240 feet. We're not saying 240 feet is equal to 15 inches. We're saying they're proportional. So yeah, 1 inch would represent some other feet. Okay. And then by table, you can draw a table like model airplane. Whoops. Model versus real. And then you can say, okay, so 1 inch in one model would be in real life would model 240 divided by 15 feet, right? And then dot dot dot, you have 15 inches. That's proportional to 240 feet, and so on. And then you can also represent it through the proportion. 240 feet over 15 inches will equal to x number of feet per 1 inch, and we can solve for x. So 1 inch on the model represents 16 feet on the actual plane, so x is 16 feet. What do you notice about the relationship between the model of the plane and the actual plane? So the model of the plane, what do you notice? And the actual plane have a proportion relationship. Yeah. And so we know that 240 divided by 15 is equal to 16. So 1 inch of the model plane is equal to 16 feet on the actual plane. Okay, so if the model and the actual plane are to scale, what do you know about the relationship between all the other parts of the model and the actual plane aside from the total height? In scale means so we can use the scale to model other planes. So if the ratio of the length of any part of the model to that part's length in the actual plane is equivalent to the ratio of the model's total length to the actual plane total length, the model and the actual plane have a proportional relationship. So that's basically what we just talked about, but we want to explain it in a different way. The ratio of the length of any part of the model to that part's length in the actual plane is equivalent to the ratio of the model's total length to the actual plane's total length. The model and the actual plane have a proportional relationship. Okay, let's look at the actual lesson examples. So the lesson essential question would be, how do scale drawings and actual measurements represent proportional relationships? Example 1, find actual lengths using a scale drawing. The island in the blueprint is 6 inches long. What is the actual length of the island in the kitchen? So we have a blueprint that's kind of like a design, okay? And blueprints are proportional to the actual one, so that you can use blueprint to actually build bigger things in actual life. But blueprint is useful because you can easily erase and change the model before you actually build it, right? So it's very important. So here we have a vocabulary word. Scale drawing is an enlarged or reduced drawing of an object that is proportional to the actual object. So you can use a double number line to represent the scale drawing length to the actual length. Remember, they're not equal to each other. Like 1.5 feet is not equal to 1 inches. Actual scale, really, the unit conversion rate would be what? How many inches in 1 foot? 12 inches. But we're not using this right now. We're saying this is proportional. The blueprint is proportional to the actual island. So we're saying in the blueprint it's going to be 1 inches. That means in actual world, that's going to be 1.5 feet long. We're going to make it 1.5 feet long for 1 inch in the blueprint. Does that make sense? Yeah, it's proportional. So use a proportion to find the actual length of the island because the blueprint says the whole thing, the length of the island would be what? Uh would be 6 inches. So the length of the island would be 6 inches in the blueprint. But that means 6 inches would be 9 feet actually, because every inch would be scaled to represent 1.5 feet in this blueprint. So actually it would be 9 feet long. So you can use proportion, right? Proportion 1.5 feet over inches. 1 inch is equal to how many feet in 6 inches, right? Because we know that this is 6 inches. And so x would be 1.5 times 6, which is 9. So the actual length of the island is 9 feet. So let's look at try it. What is the actual width, W, of the island if the width in the drawing is 2.5 inches, right? So there are steps here with the blanks. You can fill in the blanks and see if you can solve this step by step. Pause the video, come back when you're ready for answers. Okay, are you ready? So what is the proportion that you set up? 1.5 feet represents what? 1 inch. It's the same scale. And so we're trying to find W, the width, when it's 2.5 inches because in the drawing, it's going to be 2.5 inches. And so actually, in real life, we can use this scale to figure out the width, the actual width in real life, right? So 1.5 over 1 times 2.5 is equal to W over 2.5 times 2.5. So W is really 3.75. So the actual width of the island is 3.75 feet. How would the proportion for example 1 change if the scale changed? So, of course, the scale, if it changes, then the actual proportion would change, right? So if 1 inch in the blueprint does not represent 1.5, it represents something else like 2 feet or 3 feet. Then other respective proportions will also change depending on that scale, right? So scale is like the unit rate. Yeah. So the ratio on the left would change based on the scale drawings. The scale change. The ratio on the right, so like in the proportion, the ratio on the left is the unit rate, but that's if that's gonna change, and if that's gonna change, this should also change, right? So the ratio on the right could still be represented by x divided by 6. Your actual answer will change, but it could still be represented by x divided by 6 or W divided by 2.5 in our case, and try it. But the value of the variable would change because of the change in scale. Okay, so now that we have learned what the scale is and how to use that, we're going to look at more examples. Let's use scale factors to solve area problems. So the scale we looked at is the scale factor. What is the area in square yards of the deck represented by the scale drawing? So this is a scale drawing. It's not an actual house. Okay, house is not like 8 centimeters by 16 centimeters long. It's very small, right? This is a model. So you can use an equation, right, in the form y equals kx, where k is a proportional constant of proportionality. We learned that in previous topics, right? To represent the proportional relationship between lengths in the scale drawing, x and actual lengths y. The constant of proportionality k is a scale factor. So the constant of proportionality in our topic would be the scale factor, and it's represented by K. So here we want to find the actual length of the deck using L in the scale drawing. And we know, we know that the area of here would be, we don't know the area, but we can figure it out later, but that's not important. We know that the length is twice as much as big as the width, right? So we want to find the scale factor too. Scale is 1/2, like 1 centimeter to 2 yards. So the actual length L is like the actual in real life. You can use the scale factor 2 yards per centimeters, right? So this is the actual length in yards. So L represents yard. K, the scale factor, is the conversion rate. So how many yards per centimeter, right? And then L should be the centimeter, the actual centimeter in the, not the actual centimeter, but the scaled centimeter, right? The length. So in the map, the length would be 16. And then we know every 1 centimeter is 2 yards, so we can multiply that by 2. Our factor is 2. So 16 times 2 is 32, so the actual length is 32 yards. Same thing for the actual width. K times W, 2 times 8, 16. Area, length times width, so 32 times 16 is the actual length, right? 32 and 16. And then that's equal to 512. So the actual area of the deck is 512. The model will be a different one, right? 16 times 8 would be 128. So the area of the model would be 128 inches square, inches square. But the actual area of the deck would be 512 square yards. Okay, let's look at example 3. Reproduce a scale drawing at a different scale. We have students reciting the landscape drawing shown at the right for a mural. They want the length of the drawing on the mural to be 80 inches. What would be the new scale and the height of the drawing on the mural? This is the painting, and we want to paint it in a mural. So this is the smaller version, right? And then the actual dimensions would be the dimensions of mural. So what is the scale factor K that relates the actual lengths to the lengths in the scale drawing? So the scale tells you exactly that, right? It would be 4 feet per inches, so it's 4. So by the way, we want to make sure that the numerator is the actual unit, like the actual length over what it's modeled, because we want to write an equation that converts the modeled length to the actual length. So if we use unit conversions, we can cancel out our inches when it's divided by inches, right? And then we can get the actual feet, right? So think about what we're converting from to what. So find the actual length first, right? So the model length is 10 inches. So 10 times 4 would be the actual length, 40. And the height would be 8 times 4, 32. So the actual dimensions would be 40 by 32 feet. And then you can use the proportions to figure out the new scale for the mural to actual landscape. 40 over 80 would be, if 80 inches is divided by 1 inch, then how many feet would be would be in scale, right? So 80 divided by 80 is 1 inch. So 40 divided by 80 should be the scale, the feet of the scale. So 40 divided by 80 is 0.5 or 1 over 2. So the new scale is 0.5 feet per 1 inch. So right now it's 4 feet over 1 inch, but we're changing the new scale. So find the height of the drawing of the mural using the new scale. So the actual height is the scale factor times the height 8, right? Wait, uh, yeah, we're finding the model height. Yeah, so we already know the actual height, 32. So 32 is equal to the new scale, 0.5 times height. And so we need the new height of the drawing on the mural. So then it's 30. It's yeah. So this scale is for the uh, pick actual house in real life, but where you want to convert it to a mural, that's mural is still not an actual model, right? So this scale unfortunately is not meant for a mural. It's for the actual, it's comparison from picture to the actual house. So we have to go through this step to figure out the new scale and then convert it to the new size of the mural. Does that make sense? So 32 divided by 0.5 is basically 32 times 2. So it's going to be 64. So the new height would be 64 inches for the mural. So 8 times 8 is 64. 10 times 8 would be 80 inches. And so this would be the dimensions for the mural. Okay, let's try it and look at the different context. The scale drawing shown represents an existing barn. It represents, that means it's not an actual barn. The shortest side of the barn measures 150 meters. Okay, so the shortest side would be the actual length of the side. So this is actual of the barn. This is the model drawing, 10-inch. If a new barn that is 2/3 its size replaces the existing barn, what will be the scale of this drawing to the new barn? So we're not using the actual numbers. We're going to compare the scale of the drawing to the new barn. So remember, we are going to do this. We're going to go through the same steps so that we can find the new scale for the new barn from the model barn. So pause the video, come back when you're ready for answers. Okay, are you ready? So what kind of information do we have? If a new barn, it's 2/3. So we can first figure out the actual dimensions. We already know that the actual width would be 150. We just need to find the actual length. So 10 to 150 should equal to 20 to the actual length, right? So yeah, 10 times 15 is 150. So 20 times 15 would give us the same thing. That would be 300, right? Yeah. So the actual length would be 300 meters. But remember, the new barn is 2/3 its size. So we have to figure out new dimensions. So the existing barn is 150 meters by 300 meters. But then the new barn is 2/3 its size. So times 2/3 would be the new barn. So 150 divided by 3 times 2 will be 50 times 200, right? 100 meters times 300 divided by 300 times 2, 200 meters, right? So this is the new barn, and now we have to find the scale factor for the barn, the model to the new barn. So 10 inches, so 100 meters per 10 inch, or you can use this one, 200 meters per 20 inch, right? Inches. So if we they should all be the same proportions, right? So if we simplify that, it's going to be 10 meters per inch. So we have a new scale. Instead of 1 inch equals 4 feet here, the new scale would be 1 inch equals 10 inch equals 10 meters is our final answer. All right, so that's our lesson 10-1, solve problems involving scale drawings. So we learned about the scale factors and what the scale is and how it's useful. Scale factor of a scale drawing is a ratio of an actual length to the corresponding length in the drawing. The ratio is the constant of proportionality K that relates the actual figure to the scale drawing. You can use a proportion or use an equation of the form y equals kx to solve problems involving scale drawings. So that was lesson 10-1, solve problems involving scale drawings. We'll continue with our next lesson in the next video. Thanks. Bye.